Hello friends, let us establish a relation between circular motion and oscillation. Is there any link between the two? Okay, I think there must be because I have been mentioning about omega here in oscillations and omega there in circular motion. In circular motion, omega was my angular velocity or angular speed. Okay, it is the rate of change of angular displacement over there. But now here, where does the question of angular displacement come into picture? Okay, but then you must have noticed one thing, that displacement, okay, displacement over there, it was a function, it was a sine function, and sine function is it is a harmonic function. That means it has got some maximum value and then some minimum value. Okay, and it's positive as well as negative, isn't it? We know that sine theta has got the maximum value as +1 and minimum value as -1. But then again, if you find the value in magnitude, okay, minimum would be 0 and maximum would be 1, or +1 or -1 would be maximum on either side. Okay, so there is ample room for thinking that there may be some relation between that angular velocity omega in circular motion and the angular frequency in oscillation. Let us see how. I have this particle performing circular motion, okay, and this is the, let us say, our coordinate axis here. I'll change it. Okay, and all right. So now my particle is performing circular motion here along the circumference of this circle with angular velocity omega. Okay, this is my position alpha. This angle is alpha. Okay, initial position is alpha, and radius of this circle a. Okay, instead of calling small a, I'll call it capital A here, because I should not confuse between acceleration and amplitude here. Okay, so this is my initial position. Let us call this position A. Okay, and now this particle, as it is performing circular motion, it moves to this position. Let us call this position as B here, correct? And then that happens in time t, small t. Okay, so at t equal to 0, it is at A, and at t is equal to t seconds, it is at B. Okay, now this angle described here is theta. Angle described is theta. Okay, but then you know that the angular velocity or angular speed is omega, and angle described is theta, and then time interval is t. Okay, so can we say that theta is equal to omega t? Yes, I can say that, because my angular velocity is angular displacement upon time, right? All right, now okay, now what I'm going to do here is I'm going to draw a projection of this point B on my x-axis. Okay, projection of point B on x-axis. I'll call it M, capital M here. Okay, and now what happens? The particle is moving along the circumference of the circle. Then this particle, it is at B, and then projection is at M. When it moves to this position, the projection will come here. When it moves to point C here, the projection will come on the origin O. When it moves here, the projection will be here. When it moves here, the projection will be here. When it moves here, at this point, let us call this point D, the projection would be at point D, correct? And what is the distance of D from the origin? It is obviously radius of the circle, that is capital A. Okay, now what happens? So now gradually you have seen here that as the particle is moving along the circumference of this circle, my projection particle, I'm calling this M as projection particle, and it is moving in this direction, right? It is moving in this direction on the way it crossed the origin at position C here. Okay, now what happens? Now it moves further. Okay, it is performing circular motion. It is going to move further. Now when it is here, again its projection comes here. When it is here, 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 and when it is at point E, my projection will be again at origin, and this goes on, and finally the particle will reach here, and the projection will be at point F itself. Okay, and now it is not going to stop. Okay, it is going to continue moving. Okay, now what happens? Again from F it moves to A, correct? Then the projection came here, then here, and so on. So now you must have noticed one thing, that as the particle performs circular motion, okay, as the particle performs circular motion, my projection particle performs oscillatory motion like that. Correct? It starts from point F, comes to O, comes to D, again O, and again F. Correct? So let me document it over here. So as the particle, let us call this particle P here. Particle P performs circular motion. I'll say uniform circular motion. The projection particle performs oscillatory motion. Correct? Now what? Now you know that the angular speed of this particle performing uniform circular motion, it is omega. Correct? So that means this particle P is completing one revolution. Correct? In how many? In how much time? So one revolution would be, time period would be equal to 2 pi upon omega, isn't it? Correct? My omega is angular speed and t is the time period. Then omega into time period would have to be equal to 2 pi, isn't it? Now what? Now the next thing is, connecting this uniform circular motion with the motion of that oscillatory motion of the projection particle. So that means the time period of M is also same. Correct? This projection particle also completes one oscillation in the same time period. Correct? Now only thing is that here in oscillatory motion we won't call it angular velocity, but then here we will call omega. So omega is the angular frequency of oscillation. Correct? And that was the relation between circular motion and oscillatory motion. Now let us prove that this is simple harmonic motion. We need to prove that. Okay, how do we do that? Now here if you see the coordinate of point B, if it is x comma y, okay, then what would be x here? Will it not be the cosine component of that? This part is my amplitude, okay, or the radius of the circle. So x is equal to a into cos of omega t plus alpha. Correct? because my angle, total angle is theta plus alpha. And what is my theta? Theta is my omega t, isn't it? So my x is equal to a cos omega t plus alpha. Okay. Now what about velocity here? Velocity would be dx by dt, and then that would be cos of omega t. We are differentiating. Okay, so derivative of cos theta is minus sin theta. So using chain rule, okay, using chain rule, again for this basics of calculus, refer to my videos on calculus in physics. Okay, and then the differentiation of this would be minus a omega sin omega t plus alpha. And what about acceleration here? Okay, acceleration would be equal to dv by dt, and that would be minus a omega square cos omega t plus alpha. Okay, but now here if you take this a and cos of omega t plus alpha together, is it not your x? So can we write it as minus a minus omega square into x? So what? So here what you see is the acceleration of this projection particle is directly proportional to the displacement, and it is in a direction opposite to the displacement. This negative sign shows that it is acting in a direction opposite to that of displacement. And now that itself proves that the motion of this projection particle is simple harmonic motion. So that was about motion of this projection particle, and that establishes the relation between uniform circular motion and oscillatory motion. Thank you so much.